James B.J. Bjorken is Emeritus Professor at the Stanford Linear Accelerator Center with many visiting positions at leading places over the years to go along with his many awards. His seminal theoretical research played a key role in the interpretation of major experiments carried out at SLAC, and first he co-authored the proposal that there be a charm quark, as Mary Kay mentioned, and the famous Bjorken scaling was ultimately connected to the partons, the quark and gluon sector of the Standard Model. He went on to do both theoretical and experimental work on many new ideas, including the design of detectors to pick up particles produced at all the angles, 4 pi detectors, solid angle detectors. And he collaborated, by the way, with our own Dean Taylor then on experiments using some of these detectors. I have to add that, and this came up this morning again, the Reddit experience was terrific. It just connected to all kinds of things here. Some people came in from outside and mentioned this. They said the same thing that I'm about to say. We all learned our particle physics through the famous Bjorken and Drell, relativistic quantum mechanics, relativistic quantum fields, and so now we get this master researcher and educator to tell us about his present perspective on the strong interactions. Please join me in welcoming Professor Bjorken.
Thank you, Bob. But you left out one thing about the Reddit, that I was awarded some kind of gold star for one of the best responses to one of my, entries.
It's still number one on the thread.
It's still number one.
Still number one. You, sir, are the king of Reddit this morning. Until he tells you what he said.
Well, the question that was asked me was, or asked the group was, what is it that defines a physicist? And my answer was that, let's see if I get it right now. Theoretical physics is let's see, I've forgotten the words now.
We can look it up.
Theoretical physics is a socially acceptable form of mental illness. Okay. Anyway, I prepared this talk in addition to the slides with the manuscript, which I'm going to mostly read, like the old boys, like Isaac Newton used to do. They read their paper, and in front of this august group of listeners, and since you're sufficiently august, I figure I can get away with it. Anyway. So I want to begin, first of all, with an apology, because I was asked to talk about the strong interaction, and I can't really adequately address this question of the evolution of the strong interaction in this talk. And the most important reason for that is the incompetence. My personal involvement has been mainly in, as you know, in the realm of quark partons, and deep inelastic scattering. And you'll hear about that from Jerry very shortly. And the history of the evolution of QCD, of course, is much richer than that. And it's already been talked about and will be talked about some more. And that I find it very difficult to follow. I mean, so much has happened since QCD has started, and I feel really incompetent to really talk about that in detail, especially Ian Butterworth showed you a glimpse of what modern QCD parton calculations look like. Not for me. Anyway, I'm going to do my best with the strong interactions. It would be very broad brush, theme being the importance of choice of language. So in the past century of development of the theory of the strong force, descriptive language has changed dramatically. I will attempt to summarize these with the emphasis being on the value of having been multilingual while these transitions were taking place. Now, I have an ulterior motivation for organizing the talk this way, which you can see there, because since retirement about 20 years ago, I've become interested in gravitation and cosmology with an emphasis on the problem of dark energy. And I feel that being multilingual in dealing with that issue is a necessary condition, but far from sufficient for ultimate success. So the final portion of this talk will be a digression into that territory, for better or worse. It'll be a sort of preview of what is yet to come in the meeting here, but obviously from a rather amateur point of view. Where's that thing? Good. So I'll begin the story of strong interaction language at the very beginning, at the end of the 19th century. So atomic theory a la Lorentz was in its infancy, and the lingua franca of the day was owned by the chemists. And this is a physics talk, so I'm not going to talk about it. The most natural starting point here is the Bohr atom, which led to the concept of the atomic nucleus. But even with that hint, Bohr tried for 2 decades to generalize his hydrogen atom language directly, but made little progress. One needed the parallel development of modern quantum theory language, which goes under the name of de Broglie, Pauli principle, Schrödinger and Heisenberg, and eventually Dirac, to really get things off the ground. So that brings us into the 1930s, which are there. Discovery of the neutron enabled the theory to evolve into something recognizable to us today. And sketchy ideas regarding the nature of the force between the neutrons and protons began to emerge. Yukawa introduced the pion. Nuclear matter was regarded as a strongly coupled liquid. Now, the 1940s were, of course, dominated by the bomb, and the liquid drop picture of nuclear matter became quite sophisticated. In the 50s, the shell model was developed, along with a more sophisticated model of the nuclear force, controlled in large part by the phenomenology associated with the deuteron. And at Stanford, the electron scattering program led by Bob Hofstadter supplied accurate data on the size and the charge distribution of nuclei and of the proton itself. In this period of rapid post-war development, I was learning the trade as a Stanford graduate student. Anyone dreaming of a final theory of the strong interaction would only have had nightmares. Certainly was not me. By then, QED was a phenomenological success story par excellence. Even so, it was mistrusted by sophisticates like Landau, Chalane, many others, because of the divergences of the renormalization constants. To some extent, that attitude was shared by Sid Drell and myself. Sid, I think, picked it up from Vicky Weisskopf, who was very much of a skeptic, and that prevailed while we were writing those textbooks. Of course, alternative languages appropriate for a more final theory were being explored. There was the axiomatic field theory language. For axiomaticians, it was politically correct to discuss Green's functions, but not Lagrangians. And then there were the S-matrix theorists, led by Jeff Chu, and they went a step further, banished the Green's functions. And in between was Murray Gell-Mann, who in 1960 introduced current algebra in the eightfold way. And it put a spotlight on the Lie groups and the Lie algebras as a powerful method of dealing with the broken symmetries. You heard about that from Steve. And those symmetries contained within the realm of the strong interactions. What emerged as the most appropriate language for the foundations of the strong interaction has, of course, not yet been mentioned. The non-abelian gauge theories arrived during the 1950s, Yang and Mills, but they did not get much traction until the 1960s. And even then, it was much a small cottage industry. And for the strong interaction, it was typically misapplied. It was isospin. There was the obvious symmetry that deserved to be gauged. And color was far away. So the transition from the old languages to the modern QCD language very much centers around the contributions of Murray Gell-Mann, but of course not limited to him. So that story should be quite familiar, and you've been hearing a bit of it here and there today. The introduction of quarks was stimulated by the growing field of hadron spectroscopy. And one of the novelties of quark spectroscopy was the SU6 strategy of putting the spin 3/2 delta resonances in the same multiplet as the spin 1/2 nucleons. That was a rather radical idea for its time. And in my opinion, the ideas of nuclear democracy, which were promoted by Chu, namely all hadrons are equally fundamental or equally non-fundamental, and Jeff was a respected close friend and colleague of Murray's, that nuclear democracy idea made the step much easier to take seriously, to put the delta and the nucleon on the same footing. Prior to that step, the nucleons, of course, were regarded much more fundamental than a very broad delta resonance which was found in pi and nucleon scattering. Spectroscopic evidence favoring quarks was soon supplemented by the evidence from the deep inelastic scattering experiments. And it's here, of course, where I became personally involved with the story. The best I can recall after all this time, I approached the problem from a multilingual point of view. Steve was very important in that. His sum rules were very much of a strong motivation. And those, of course, again, emerged from Murray's pioneering work, and they comprise the most reliable tool. But that did not go far enough. One had to, especially for SLAC and also for neutrino experiments that were floating around, that did not go far enough, and one needed to know more about the details of the structure function and how these sum rules would converge and how long it took in energy to make them converge. So high energy asymptotic behavior at fixed invariant virtual photon momentum required the use of Reggie-Pole theory. There was experience from the atomic and nuclear physics heritage sum rules, which were structurally similar to those emerging from Kern algebra, and those suggested the notion of point-like constituents, but only at a rather speculative level. My mentor, Sid Drell, wrote papers with Charlie Schwartz on sum rules for electron scattering from nuclei, which were essentially parton models at the nucleon level. The relationship of resonance contributions to continuum behavior, which now known as Bloom-Gilman duality, was part of my own theoretical toolkit, which I owe to a visit of Jerry, who asked me the right questions. And I well remember it. I know, Jerry, you remember it?
No, I don't remember the question.
You asked the question how the resonance Q-squared dependent would relate to the continuum behavior in the threshold region. And I hadn't thought about it. And so I came up with Bloom-Gilman duality at that time. So I knew about it when Bloom and Gilman published their papers and did it right. And then there are the descriptions using light cone coordinates, which were also an important ingredient. And of course, thinking about neutrinos as well as electrons was also of major importance. So in hindsight, my own use of those theoretical tools, however, was quite clumsy. I look back and my gosh, didn't do a very good job of it. There was no full commitment to any single one of them. But my main emotional commitment was that the set of deep and elastic experiments that were going on, which were not at all sexy for their day, were really going to be very important. And the thing I value the most in terms of my contribution is pushing the experimental group to make sure they were, help make sure that they were done well and thoroughly. 1970s were truly revolutionary, and I will not even bother to review all the highlights. By the end of that decade, QCD was very well established despite a handful of holdouts, and that included me. I would drag my feet on the electroweak theory, on fractionally charged quarks, QCD, the whole works. And always been something of a contrarian, and I don't regret that at all, even to this day. Time to move on. So the 1970s were, of course, very truly revolutionary. You've heard already about them, and I'm not going to even bother here to review the highlights. By the end of that decade, QCD was quite well established, despite a handful of holdouts, and that included me, as I said. So now I'll turn to the descriptive language of QCD itself. So it naturally divides into the short-distance partonic language and the long-distance hadronic language. It can also be divided into QCD light and QCD heavy. QCD light is a Wilczek term, and in QCD light, you only keep the up and down quarks and throw the rest away. For QCD heavy, you keep the top and bottom quarks and throw the rest away. And for simplicity, you forget about the electron-weak interaction and look at QCD just by itself. In both light and heavy versions, the short-distance world is controlled by parton model ideas with, thanks to asymptotic freedom, Feynman diagram perturbation theory, the appropriate descriptive language. For QCD heavy, long-distance confinement limit becomes a string theory. The quarks are connected by it. In addition, closed strings provide a glue ball sector as well. Nice stable glue balls. For QCD light, strings are both broken by light quark pair creation. And much more important is the presence of the chiral condensate of the up and down quarks with the emergence of the nearly massless Goldstone pions a la Steve's talk. And the descriptive language nowadays here, it can be taken as the Gasser-Leutwiler effective action, for example, and the generalizations thereof. So it's still a challenge to derive that effective action from first principles. In principle, all those nuclear physics languages like liquid drop, shell model, nucleon potential, nuclear matter, and so on and so forth should be derivable from this generalization of the full Gasser-Leutwiler action that would have, for example, rho meson exchange and other things like that. And for QCD heavy, the string tension, the string properties, likewise should be derivable from first principles. And I think this problem is probably in better shape than the QCD light problems, although I think there's plenty of work to do in the future to see whether or not you can really create a description of the entire strong interactions just starting from the parameters in the QCD Lagrangian. If you think it's a closed subject, wrong. It's very much an open subject and plenty of opportunities to work to make that happen. And there's lattice QCD out there that is a foot in the door, but I think it's only a foot in the door compared to what this visualization requires. So that's as much as I want to say now about the strong interaction. So let me move on to wilder stuff and languages for general relativity in cosmology. As I said, since retirement, I've become interested in GR and cosmology, which also is expressed in a variety of languages. But it will be no surprise that the overwhelming favorite language is the Riemannian language introduced by Einstein himself, the ultimate guru of the subject. And not surprisingly, I will here concentrate on alternatives. Major alternative goes under the name gauge gravity, and I'm especially drawn to it because there it is up there. It's an 031 gauge theory. 031 is just the Minkowski symmetry of space-time, and and so it has an affinity to, very close affinity to rotations in 4 dimensions and ordinary rotation in 4 dimensions, which is good old standard model type of territory. Now, variants of gauge gravity include the geometric algebra version, which is in Cambridge, England, led by Lazenby, Duran, and Hesnes, and various other people have made big contributions to it. It involves Clifford algebra language. And there's an 041 generalization by McDowell and Mansouri down there somewhere. And you can see the lingo in there. I don't want to describe all that symbolism here. This is not the appropriate time to do that. But you can, if you run vertically, you can see there's a similarity between the nomenclature, and there are distinct differences as well. But I mentioned that the McDowell-Mansouri extension, which is especially important. There's well, let's see, I'm getting ahead of myself here. So Riemannian language features a metric tensor, which has 10 G mu nu, which has 10 components. And from it, you do geometry. The left-hand side of the Einstein equations are built from G mu nu and its derivatives alone. And the energy momentum source term on the right-hand side is found by varying the source components of the action with respect to G mu nu. And so that's the most efficient. The gauge gravity language is more extravagant. There are 24 components of the 031 gauge potential, 6 times 4. 4 for x, y, z, t, 6 for the gauge degrees of freedom in the adjoint, and they go under the name of spin connection, little omega on the screen there. In addition, there are 16 additional degrees of freedom called the Vierbein, or frame field, and the metric tensor of Riemannian gravity is essentially the square of that Vierbein. There's a formula up there, I hope, for it. I didn't write it down. You multiply it by itself, contract with the metric tensor, the Minkowski matrix, and get G mu nu out of it. McDowell-Mansouri extension synthesizes the Vierbein and the spin connection into 10 times 4, 40 components of a 041 gauge potential A. And this leads to an elegant form of the Lagrangian, which I did write down, I hope. Up there, yes, in the blue in the corner. I can almost point to it. Not quite. And so it's quadratic in the field strength, which is constructed in the usual Yang-Mills way from the gauge potential A. So when it's decomposed down to the aforementioned gauge gravity description, one finds as a necessary consequence the existence of it'll be on another slide here, of a dark energy contributor in addition to the gauge gravity version of the Einstein action. You'll see that later. Another singular feature of both these descriptions is that they're spinor-friendly. It's relatively easy to include quarks and leptons in the description, which is not the case for Riemannian gravity. If you pick up a standard GR textbook and search for the chapter with having to do with spinors, you'll have a hard time finding it. It's usually in the back of the book. And if you do succeed in finding it, you'll learn that the Riemannian language used in the preceding chapters of the book is inadequate for the job. You either find a crash course on gauge gravity or a reference to some other source material. We all look forward to the modern-day version of Einstein's dream, namely the unification of general relativity with a standard model. And I find it quite curious that given the prominent role of spinors in the standard model, there's such an adherence to the Riemannian version of GR. Finally, before going to the next slide, I should mention the loop gravity program. This is Ashtekar and his followers, Lee Smolin and others. Other than to say that the prominent feature of it is its description of the gravitational vacuum. They have a tangle of string segments and nodes called a spin network. And its prominence suggests to me that vacuum topology in GR may well be an important fundamental feature of the description. This opinion is reinforced by the structure of the McDowell-Mansouri action. When it gets deconstructed into the 031 gauge gravity language, there is, in addition to the aforementioned Einstein and dark energy terms, a leading term, which is topological and does not contribute to the equations of motion. Maybe that's on the next slide. I forget where it is. There it is. So that leading term is up there. It's called the Gauss-Bonnet term. Lagrangian is decomposed into those three terms. Euler, the Einstein term, which gives you the equation of motion, and necessarily a cosmological constant term with the right sign. So this McDowell-Mansouri language has attracted me for quite some time, largely because it requires the existence of dark energy. It's fermion-friendly. In addition to the Einstein and dark energy contributions to the action, it has that Euler invariant. My study, I've spent some time studying this quantity n, which is because it's a topological term. It doesn't contribute to equations of motion, and could be written that way, where n is the natural quantity. And I've studied that in some detail, which I call that darkness. And the study's actually out there in published form in Annalen der Physik about 4 years ago. And in dark energy dominated space-time, like called de Sitter space, the density of darkness is essentially 1 per cubic Fermi. And that's because of this huge coefficient of 10 to the 120 out in front of the term. So this distance scale is 1/3 of the way, logarithmically speaking, between the Planck scale of 10 to the minus 33 centimeters and the cosmological scale of 10 to the 28 centimeters. So for better or worse, the Zeldovich scale, which I call it was first noticed by Zeldovich, is emergent from pure GR considerations, and it plays an important role in how I think about gravity in general. As you go back in time, cosmological time, this darkness density increases. It was Planckian when the hot Big Bang temperature was ordered as 100 MeV, which is again the Zeldovich scale. So that suggests to me that this description is at best an effective field theory of limited applicability. Something better is needed to describe cosmology at earlier epochs. And while this sounds like a deficiency in the description, I'm not convinced that it really is. And this opinion slightly reinforced by yet another personal speculation. This aforementioned Gauss-Bonnet term in Lagrangian is a parity-conserving variant of the E dot B terms, anomaly-type terms, which are present in QED and QCD, and which you heard about earlier in the afternoon. Those go under the name of Pontryagin, not Euler, generated by the triangle anomalies. But the coefficient for this McDowell-Mansouri Euler term is, as I mentioned, the 10 to the 120. Clearly, one starting in the middle for all these reasons. So there's a prehistory to this this description. And I've tried to understand the 10 to the 120 as 10 to the 20 raised to the 6th power. And each factor of 10 to the 20 is contributed by a large compactified extra dimension, which is 20 powers of 10 larger than the Planck scale, which is a Zeldovich scale of 10 to the minus 13 centimeters. So this is not the place to go into detail in this regard. Suffice it to say, with the 6 extra dimensions, the McDowell-Mansouri action is naturally extended all the way to an 091 gauge theory. So I'm heading up into the stratosphere in a big hurry. Now those 6 extra dimensions are clearly politically correct to introduce because that sounds like string theory. The 091 might have evolved in very early universe cosmology from an 010 starting point by Hartle-Hawking transition. So this is advertised to be especially user-friendly when the Hartle-Hawking transition, when using the language of gauge gravity. So nudged along by this string theory ideology, it's an attractive option, at least for me, to append the 010 standard model gut group to this description. And so now I've got an 010 on the gravity side and 010 on the standard model side, and up we go to 016 cross 016, which is right in the middle of string theory territory. So again, I'm not, even though it's extravagant, it's not politically incorrect to do that. I've recently found myself in this rarefied atmosphere for another much more down-to-earth reason. One of the outstanding problems facing the standard model is a family problem. From current, what I mean by family are family triplets like up, charm, top, down, strange, bottom, E, mu, tau. That's different from flavor. Flavor is SU6, it's SU6 of the 6 quarks. If you talk about flavor, the electroweak group is a subgroup, and the family group's also a subgroup of the flavor group. So anyway, that's what I mean by family. It can be defined from Kern algebra alone, a la Steve's talk. And once you identify families that way, it seems to me all theorists should remember to often ask themselves the following 3 questions. Question 1, are there non-trivial family multiplets in the dark matter sector? Yes or no? Are there non-trivial family multiplets in the Higgs sector? Yes or no? Are there non-trivial family multiplets in the gauge boson sector? Yes or no? Here are 8 options, very precisely defined for the future of particle physics and gravity. All 8 should be explored. Choose one and do something, please, about it, you young people. Now, the answer to the question for the Higgs sector and the gauge boson sector are most likely correlated. If you could gauge family, the family group, then you probably want to gauge the Higgs, or want to put family into the Higgs sector, just to make those gauge bosons massive. So it's really 4, not 8. Anyway, I choose to answer all 3 questions affirmatively. Therefore, the family group is gauged. And so between my 010 cross 010 and 016 cross 016, that's a natural place to put in the family symmetry. easily said and not easily done. I have not succeeded in constructing an attractive model. So anyway, these grandiose visions have, somewhat surprisingly for me, become rather closely aligned with those of string theory. And I'm not a member of that community, never have been attracted to, for example, to work on or think about weak scale supersymmetry. But all I need to do is assume that SUSY is broken at the Gutter-Planck scale, and then it's very easy for me to think about jumping on the bandwagon. So I personally keep that option open. How are we doing on time?
Fine, you got plenty of time.
Okay. I'm most of the way through. But if you think this is speculative, it gets worse. So, last subject is dark energy. And in the last year, I've been pushed in another direction. And this involves a very interesting new idea involving the nature of dark energy. I've been obsessed with that problem all along. But this is due to Alejandro Perez and Daniel Sudarsky. They attribute the present-day dark energy to a very primeval Planck-scale noise source, which originates in the fermionic sector of the theory. The limit of a scale-invariant description, this noise did not create a phenomenology, but given their fundamental present premise, the important mass scale that intervenes must be fermionic. So here's the picture. The pictures I should describe a little bit. Here's my favorite way of describing the history of the universe. A is the F.R. Friedman Robertson Walker scale factor, A of t. You better know what that is. It expands, tells you how big the universe, dimension of the universe is at any given time. And A dot is just the time derivative. So it's like plotting velocity versus coordinate. So during inflation, log A dot grows linearly with log A. At the end of inflation, you have this reheating event. You go to all the dark energy is converted into plasma, very hot, and then it cools off with radiation dominance until the very near future. And then now we're about to enter reinflation with dark energy dominating the expansion a second time. Over here, I've plotted you don't find that plot very often in the literature, unless I write something. But the one you do find more often is plotting the log of the Hubble parameter, A dot over A, versus time. And so their picture is that, well, forget about what happened in inflation, that the present-day dark energy originated during the electroweak period, when the temperature was somewhere around the electroweak scale, due to some kind of noise source, which originates in the fermionic part of the theory. In limit of a scale-invariant description, this noise does not create phenomenology. And given their fundamental premise of important mass scale, which intervenes, must be fermionic, top quark contribution stands out as prime candidate for implementing their mechanism. Now, these are only words, and an equation expressing this idea is needed. And during the radiation-dominated hot Big Bang, the expansion is scale invariant. Trace of the energy momentum tensor vanishes, but it will be slightly broken by the top quark contribution when it comes in, but not enough to affect significantly the Hubble constant at that time, when the temperature was hundreds of GeV. So they write down an equation which is governed by the growth of the lambda is governed by the square of the trace of the energy momentum tensor. The square is chosen because of the hypothesized statistical noisy nature of the source. So this contribution is largest shortly after the top quark acquires its mass by the Higgs mechanism. As the universe expands, that source term rapidly dies off, and you get this behavior shown on the picture. Now, when you grind out the equation, it turns out that the answer scales to the 7th power of the top quark mass, which is 17 powers of 10 below the Planck scale. And therefore, the prediction for lambda, which is on the next slide, I guess. No, that's mine. Prediction for lambda comes out to be 10 to the minus 17, which is the ratio of the electroweak scale to the Planck scale, raised to the 7th power. You do that 10 to the minus 17 to the 7th power, 10 to the minus 119, which would be compared with the right answer, which is 10 to the minus 120. Close enough. So for me, this is eyebrow raising and worth thinking about some more. And Paris and Zdarsky sent me a draft of their work, and I provided some criticism. They accepted the criticism, rewrote the draft, and I ended up being a junior author on that paper, which is actually on the archive. If you want to know the details, it's there. And since then, I've had an obsessive interest in the core idea of what the nature of that primeval noise is. So I've chosen to investigate the problem of inflationary dark energy rather than their choice of present-day dark energy. And so I pick up on these darkness ideas and ideas I've had in the past and assume that, first of all, there's a presence of those 6 extra compactified extra dimensions, and that there's a presence of a condensate of massless vial fermions which couple only to gravity. And during inflation, in order to have a chance of making the equations work, the size of the extra dimensions shrink in such a way that the total 9-dimensional volumes of space, the 3 for physical space and 6 for the extra dimensions, that volume does not change during the expansion. So the gauge gravity equations which emerge are non-trivial. I'm still grappling with the details. They have a kinship with what's called the Kastner metric, which long ago led Charlie Misner and others to study what was called the mixed master universe. So those of you who are in the trade might recognize some of those things. So some of the features of my version are interesting and appear to be robust. Appears a modified version of the FRW equation. The usual one states the square of the Hubble expansion parameter, A dot over A, is given by a sum of contributions from dark energy, from curvature, radiation, matter, textbook stuff. The version appears here for inflation only, equates the Hubble parameter itself to the condensate density. So the Hubble parameter is a condensate density in natural units. Actually, the density divided by the square of the Planck mass, instead of the energy density being divided by the Planck squared mass. So this implies that the condensate density is at the very least closely related to the aforementioned darkness density. So I'm looking carefully at the possibility there's a statistical property, this fermion condensate, which can be related to Perez and Zdarsky's noise source. I think I'm going to skip to the end here because we're getting close. But in any case, it's clear that the starting point I have is really in the middle of a larger story. That during inflation, this size of the universe increased by a factor of 10 to the 22. The size of each extra dimension decreased, therefore, by half as much, 10 to the 11th per extra dimension, in order to keep the total volume constant during inflation. And since we assumed that the extra dimensions, or since I do assume that the extra dimensions did not change thereafter and are large, of order 10 to the minus 13 centimeters, that means that these extra dimensions at the beginning of inflation were gigantic, like 1/10 of a millimeter. But then those extra dimensions shrunk during inflation, the universe expanded, and there's a period almost at the end of inflation and very near reheating where the extra dimensions are the same size as the physical dimensions. And there's a hope and an expectation, a dream, that this is close enough in time to the reheating event. It opens the possibility of this crossover actually driving and being a trigger for reheating, which is an outstanding problem of cosmology as to how to describe the phenomenon of reheating. So now I summarize. So in the old days, QED and Q general relativity stood out as prototypes of truly fundamental descriptions. And so the idea of a final unified field theory was credible, with hopes, at least for Einstein, that a theory of everything was principle within reach from a modern perspective. I think this hope looks much more unreasonable. The beauty of standalone QED itself has been compromised by the emergence of the SU2 cross U1 electroweak theory, which we celebrate at this meeting. With all due respect to Steve Weinberg, I find that what he did made QED less beautiful. I do not find the Weinberg angle especially beautiful, even though the consequences, of course, of what he did are profound. Another desideratum of the old days was not only renormalizability, but mathematical consistency in the far ultraviolet. As I already mentioned, QED fails that criterion, although QCD passes the test. But nowadays, such criteria seem to me, at least, much less urgent, and the concept of effective field theories is much more prevalent now than it was in the old days. And one reason is the ubiquity of such theories in condensed matter physics, where symmetries such as relativistic invariance can emerge from fundamental Lagrangians, which possess much less symmetry. So nuclear physicists of the 30s might well have worried about renormalizability of the Yukawa theory of the nuclear force. But no nuclear theorist today is going to worry about the renormalizability of the Gasser-Leutwiler effective theory of the nuclear force or its future generalizations. I even regard my grandiose O16 cross O16 version of gravity plus standard model as an effective field theory. Space-time itself may well be emergent, and there are for me several levels above that totally speculative O16 cross O16 description you can see there. The next might be string theory. Above that could be M theory, where strings are emergent in a way perhaps somewhat analogous to how strings emerge in QCD heavy. And above or at the M theory level might be a full digitization of the entire theory, a la Steve Wolfram or Gerard de Tooft, for example. Maybe this, maybe that. But for me, just dealing with the dark energy problem itself is quite enough to last me for the rest of my days. Thank you very much. Sorry.
So we have a few minutes before people are desperate for coffee, but I think that there's
one of many questions I could ask. Are you saying that the dark energy we see today arises from compactified extra dimensions of size of a Fermi?
They're involved, yes.
Aren't
In my version, yes. That the dark
extra,
energy or inflation.
Right, aren't extra compactified dimensions of order of Fermi ruled out by the lack of particles with momenta at the LHC?
Say it louder.
Doesn't the LHC rule out compactified dimensions?
It depends how they gravitate. I'm not sure the way I'm going to make them gravitate would be the same
particles
as the way
with
you
momentum. Any particle described by an effective field theory in a higher dimensional theory, if you compactify some of the dimensions, will have excited states with Kaluza, with momentum of order
when I listen,
1 over the radius, and that's already ruled out, isn't it, by LHC?
We have to talk about this offline, but my 6 extra dimensions in McDowell-Mansuri are totally passive. no dynamics associated with it that I can see.
But you have fields propagating. You have the fields of the standard model, for example, live in these 10 dimensions, correct?
They're moving in and out of the extra dimensions.
Will have excited
Maybe,
modes
maybe.
with momentum
We should discuss
quantized
it
in
some
units
more.
of 1
Yeah.
over r, and LHC probes dimensions down to 10 to the minus 18 centimeters.
Okay, I hear what you're saying. Thank you.
The question, what did you think about the vacuum state and
Yeah.
the role it plays when you quantize general relativity? Because that's much more complicated than in special relativity,
Yeah,
where you know what the vacuum state is and it's always the same. In
right.
gravity, it's much more subtle. And this would have to do with the fact that even the vacuum state has some energy which you wouldn't have expected. That's this dark energy you talk about.
Right. I would paraphrase what you're saying in the following way: that we have we have already on the books a history of discretization. It's called the quantum theory itself. In the time of Planck and Boltzmann, right after the Planck formula was created, it's clear, at least to those pioneers, that it involved the discretization of phase space. And Boltzmann himself was already, and de Gibbs were already discretizing phase space in order to count states. And then you ask, and phase space is discretized in the quantum theory, but it took almost 30 years, 25 years or so, before the rule for how to do it was created by Dirac, and he did it in one sentence: replace Poisson brackets with commutators, which is not the obvious answer that would be there at the time of Planck and Boltzmann. So I agree very much, and I think that to go from where we are now to a view of discretization will involve at least as much subtlety and thinking outside the box as it did for those pioneers in phase space. But this is something I want to learn from you rather than the other way around.